In the last video, we talked about the idea of concentrations of solutions, and I mentioned that we can use them in reactions. So let's take a look at an example reaction and how this could be relevant for us figuring out some stuff. So let's say we know that this balanced chemical equation is true. That two potassium chloride molecules that are aqueous, that means they're dissolved inside of a solution, or dissolved in water because aqueous means water. If we add those to one lead 2 nitrate, and it's aqueous, and we mix these things together, what'll happen is we're going to form a solid PbCl2, and we'll talk about how by the end of these videos, you'll be probably, these videos this week. We'll talk about some next week as well, but you're going to be able to actually predict this is what it'll make soon. And we're going to add to that 2 KNO3 that stay aqueous. So you don't know that yet though, so I'm just going to tell you what the reaction is. So if we combine 2 KCl molecules with 1 lead 2 nitrate, we get 1 lead 2 chloride and 2 potassium nitrates. It's already balanced, and you can check that if you want to, but I'm going to go ahead and tell you it's balanced. You don't have to worry about that. Also remember that we're probably not working with just 1 or 2 molecules, so you can also say that 2 moles of KCl plus a mole of lead 2 nitrate makes 1 mole of lead 2 chloride and 2 moles of potassium nitrate. So then let's ask this question. What volume of let's go with 0.150 molar KCl would be needed to completely react with 0.200 liters of 0.200 molar lead 2 nitrate. Make sure that looks like a 2. And that looks like a 2. So first, without having to do the actual math, let's think about what they're asking. They're saying we have one solution that we know how much we have. We have 0.2 liters of 0.2 molar lead 2 nitrate. So this is, let's say we've got a beaker. Part of my beaker disappeared. There's the beaker. So in this beaker, we have 0.200 liters of 0.200 molar lead 2 nitrate. And then the question asks us, we want to add some KCl, but not just any amount of KCl. We want to add the exact amount of KCl that would be needed to completely react with this lead 2 nitrate. We don't want to have extra laying around. We don't want there to be a limiting reactant. We want there to be exactly enough of both to complete the reaction. That means we're going to need to find out something about the moles, right? Because that's the only way we know how to go between one compound and another. So we need to get to where we know how many moles of lead 2 nitrate we have, so we can then find out how many moles of KCl we would need to react with that. So my goal is I need to get to moles, because once I'm in moles, I can go between my different compounds. So my strategy is going to be, we know our volume of our lead 2 nitrate, so we want to get that to moles of lead 2 nitrate. And we're going to do that by using our molarity, because molarity lets us go between volume and moles and volume. Well, once I'm in moles of that, then I can go to moles of KCl. And if I want to go between moles of one compound and another, I can do that by using my balanced equation. Now the problem doesn't ask us for moles though, it asks us for volume. So we've got to go back to volume units, but this time of KCl. So I use the molarity of KCl to go between those two. So now I have a strategy. They gave me volume, and I can use molarity as a conversion factor to get to moles. I can then use the balanced chemical equation they gave me to get to moles of the substance I want, and then I can use the other molarity provided to get me to the volume of the solution I want to know. So now, let's set this whole thing up. So we're going to start with our 0.200 liters of lead 2 nitrate. Now, we're going to go to moles instead. So they told us our concentration was 0.2 molar as well. That means for every 1 liter, we're going to get 0.200 moles of our lead 2 nitrate. So now, once we're in moles of that, now you could do this one step at a time and solve like 4 or 5 written problems, But this is why I like to do these all as one big step, is it gets really cumbersome as you do 3 or 4 conversions in the same problem. So I'm just going to do them all in a big line. So our next step is we want to go from moles of lead-2 nitrate to moles of KCl. From our balanced chemical equation, we don't have a number in front of here, so that's an understood 1. So that means every 1 mole of our lead-2 nitrate is going to lead us to getting 2 moles of KCl. And then to finish it up, the problem wants to know what's going to be the volume of our 0.15 molar KCl. So we know every 0.150 moles of KCl, we're going to need 1 liter of that solution to get that many moles. So if we check our units, our leads, nitrates, liters cancel, our moles of lead-2 nitrate cancel, and our moles of KCl cancel. So now, I got a number of things to plug in. So let's put all this in. And when I do that, I'm going to find that I need a total of, now let's see, it just said volume, so I'm going to report it as 0.533 liters of KCl. You could also report it as 533 milliliters. Both would be fine if the problem didn't ask for a specific unit. And that's how much KCl I'm going to need to be able to do this reaction. So this is an example of how we can take all those ideas we learned about conversions with chemical equations and actually making reactions. But the one step we change here is in the last chapter, we had solids. So with those solids, we were given grams, and we could use molar mass to go between grams and moles. But now the change is instead of using molar masses, we're now given volumes. And with those volumes, we can go from moles to liters. So we can use that molarity thing to take a volume and go directly to moles. Now this doesn't mean the stuff from the last chapter doesn't also apply. So I'm going to take the same equation. We're going to do a second question that's related, but not exactly the same. So we're going to erase. This is not the fastest eraser there is, but I want to keep the top of the equation so it's worth a kind of slow erasing that I awkwardly erased that I could have talked during earlier. I guess I'm still technically talking now, so that works. Man, I will figure out a better way to erase half a slide sometime in the future. I'm sure there's some highlight tool that I just don't know, and I'm sure there's at least one person out there screaming at me, your computer going, Dr. Leslie, this is so slow. We could totally do this better. But this will work well enough. So what we want to do is we want to take this reaction, and we want to ask a different question. And I did not mean to delete my P. I can bring it back. So now, we'll make it a different question too. So what we want to do is we want to show that it's not just molarities that we can use. We can also use the molar mass stuff from last chapter in a similar way. So what we're going to say, don't want to make this challenging. Yeah, let's make this a little challenging. It'll be good practice. So what we're going to do is we're going to come up with the mass component. We're also going to practice from our last chapter our limiting reactant stuff. So what I want to ask you is if 0.0 milliliters of 0.100 molar KCl is reacted with, let's say, 100 milliliters of 7.075 molar lead-2 nitrate, how many grams, not grams, grams of lead-2 chloride are formed? So our question becomes, we still have to do the molarity stuff, but at the end we've got to get to grams of lead-2 chloride rather than a volume. You'll also notice they told us how much we had of 2 different reactants. If they give you both the volume and the molarity, that's enough to find moles. So since they did that for both the KCl and the lead-2 nitrate, you have enough information that you can find out how many moles you have of each. And if we know how much we have of multiple reactants, we have to check all of them to see which one we run out of first. So for this problem, I'm going to check both of them, and we're going to see, do we run out of our potassium chloride first or our lead-2 nitrate? Because that will give us our theoretical yield, and then we can convert it to grams to finish the problem. So let's start with our KCl first. Remember, we solved basically 2 separate problems where we go, oh, what if this is the one we ran out of? And we find out, and we get 2 different answers, and we compare them. So KCl, we have 100 milliliters of it. At this point, we're far enough along that I'm okay if you can go directly from milliliters to liters, you can just write that out. And if you're not sure, you do an extra step. Remember, there are 1,000 milliliters in a liter. But I'm going to go ahead and just write that this is 0.100 liters because I think we're far enough along that it's okay that I should assume that you could be able to do something like that. So, if not though, it is okay to do the extra step and have to convert from milliliters to liters. I'm just trying to introduce some of the shorthand that we use long term. Like as a chemist, eventually you've done enough milliliters to liters conversions that you can say, okay, I moved the decimal 3 times in my head, and that's a-okay. If I had to go microliters to liters, or microliters to milliliters, let's say, there's a better chance I might write out that work, but once you've done it a lot, you'll get used to any one you work with. But if you're ever unsure, just write out the step and you'll be okay. So we've got our 0.1000 liters of KCl, and I know that for every 1 liter of KCl, I get 0.100 moles of KCl. And the problem wants to know about PbCl2. For every 2 moles of KCl, we make 1 mole of our lead 2 chloride. So now let's check how much this one makes. So this is going to make 0.00500 moles of lead 2 chloride. And if you put it in scientific notation as 5.00 times 10 to the negative 3, that'd be a-okay as well. Now we also check our lead 2 nitrate. So here we now have we also have 0.1000 liters, but we have a different concentration. And at first you might just, when you're quickly glancing, go, oh, that concentration's lower. It must be the limiting reactant. But we have to watch our balanced chemical equation because it won't be in this case, even though it's got a lower concentration. So for every 1 liter of our lead 2 nitrate, we're going to get 0.075 moles of our lead 2 nitrate. Now, from there, we're going to go with the fact that for every mole of this lead 2 nitrate, we're going to make 1 mole of lead 2 chloride because it's a 1-to-1 rather than a 2-to-1. So when we put all that in, you're going to get that this is going to make 0.00750 moles of lead 2 chloride. That means this is going to be my theoretical yield because KCl is my limiting reactant. The last step of the problem is it asks for grams. So I'm going to go down here, and I'm going to start with my 0.00500 moles of lead 2 chloride, and I'm going to convert it to grams. Do that. Get my periodic table back out. Look up my molar mass. Times 2. Lead, where are you, lead? I know you're here. There you are, lead. It's in the P block, in case you're looking. It's underneath carbon, so it's really far down the road. So, we have that every 1 mole of lead 2 chloride has a mass of 278.1 grams. So if we multiply that out, sorry about switching screens, I will get better at that. My little pen has a button that does it I don't mean to press. We multiply that, we have 3 sig figs, so 1.39 grams of our lead 2 chloride is how much we would be able to make. So, this is an example of about as hard as these questions can get in terms of arithmetic. It's a limiting reactant problem, so you have to check twice. It's got multiple polarities, and then you need to convert something to grams as well. So you'll notice we can use the stuff from the last chapters, moles to grams, and we can use the moles to liters conversions in the same problem. You pick which one you use based on the types of information you want. So if you want to get the mass of a solid you're going to make, you'll use molar mass. If you want something about the volume of a liquid that's a solution, then you'll use molarity in liters. So you have to pick it out based on context, what information you have available, how does that match up with what we're working with. Now, to finish, and we will practice these some more in class, as well as I'll make sure there's homework on these. This problem, I'll admit, what we just did involves a whole lot of ideas. And especially if you weren't super comfortable with limiting reactants in the last chapter, this can feel pretty challenging. I'll say it up front. This is definitely something you have to practice some, but I think it's very doable as well. It's still very systematic. You'll notice kind of like when we did things like empirical formulas, there's a pattern to it of how you do these conversions. It's not that tricky. It's just remembering all the steps and sort of learning the logic for them so you're not trying to memorize a pile of steps. Like I'll admit, I can do these, but I don't have a memorized checklist where I go, oh, do step A first, then do step B, then do step C. I try to learn, okay, what's the reasoning? and then I use that to try to solve these. And that's why I'm always going to try to say out loud as I'm going why I'm doing what I'm doing. Now, there's one more idea I want to talk about to finish up this area of solution calculations. And then after that, we'll have some videos on some conceptual stuff related to solutions, how to make some of the balanced chemical equations, how to do some more predictions. But the last thing I want to talk about is a concept called dilution. Now, I want to start this by saying dilution is practically useful in a number of cases. That's why we're going to give you a very specific equation that is useful when you're diluting something. However, I'm giving you an equation here that because it looks like an equation that we haven't had one in a while, people like to apply it to all kinds of problems. This is relevant for dilution questions. This is not a way to solve, for example, the problem we just did. The problem we just did, you had to figure out which one is your limiting reactant. You had to do a bunch of conversions. There is no magical equation for that one. Dilutions, there is an equation. And the reason we can use this is in a dilution, what you're doing is you have some container and it has some amount of solution. So this is, you've got some volume and some molarity because this is your initial solution. And then what you're going to do is you're going to take some container, or we've got some hose, let's say. This is connected to your faucet or something. This is awfully drawn, but it's okay. We're going to add solvent. So you're going to dilute it by adding more of the solvent, but you're not going to change how much solute is in it. This is the only reason this question works. If you're combining two solutions and they each have some solute in them, it's not a dilution solely anymore, and this equation isn't going to work for you. The reason this comes up practically so often is it is easy to transport a chemical that is very concentrated. Either we're talking about just to the school itself or to wherever you're working, right? If I need sulfuric acid, I don't want to have to travel it in a smaller all the volume is what makes it heavy. So if I have a really dilute sulfuric acid and I ship it, that's way more expensive to ship than if I take a really concentrated acid. Now, there are some extra safety precautions with some concentrated solutions. That's why some things you buy will still be dilute. But if it's possible, and I need a bunch of it especially, like if I only need a little bit, it's fine to order it dilute. I'm only going to use a 500 milliliter bottle. I don't need to buy 5 milliliters and dilute it. It's fine. But if I'm going to use liters and liters and liters of this, it makes sense to buy it concentrated and dilute it to what I need for lab. It's what we do to prep a lot of the chemicals in our labs, for example. You guys work with very dilute solutions. We might buy the solution, the acids or bases already made, or we'll even have them as a solid form, dissolve them in some water, and then dilute them. Like we'll make a concentrated version, then prep a bunch of dilute ones for you guys to actually use. So purely as a scientist, whether you're a chemist, a biologist, a geoscience person, whatever you go into, it's practical to know how to take a solution that is concentrated and make it dilute. So the way we do this is we added this solvent. When we added this, we get a new volume, and we'll have a new concentration. So their relationship is that M1V1 equals M2V2. So what does this mean? Let's say I have a bottle of 20 molar HCl. I can't remember exactly what concentration pure HCl is. I think it's higher than that, but not a whole lot higher. And I want 500 milliliters of 1 molar HCl for a reaction. Maybe I'm using it for something in lab to show you guys. And I want to make a bottle of that. How much concentrated HCl do I need? And by concentrated in this case, on context, I mean the 20 molar. So how much concentrated HCl do I need? So in this case, we have to see which part it is we don't know. It won't always be the same thing. So here, you know you're using the concentrated one. So that's our M1. We know that. M1 is equal to 20.0 molar. We don't know how much we're going to use, though. That's what we're starting with. We're not sure what V1 is. But we know in the end, we want our concentration to go down to 1 molar, and we want our total volume at the end to be 500 milliliters. Or, I'm going to put that as 0.5000 liters. So now, I need to figure out how much am I going to use of my concentrated version. So, if our equation is M1V1 equals M2V2, and we want to solve for that's supposed to be a 2, we'll rewrite it. We want to solve for V1. I'm going to divide both sides by m1. And so when I divide both sides by m1, that'll make it cancel on this side. And that will give me that v1 equals m2 v2 over m1. So now I can plug in all my values. So I'm going to plug in my m2 is 1 molar. My v2 I'm going to plug in as 0.500 liters. And then my m1 is, by concentrated version, it's 20 molar. So the molarities cancel. And I plug that in. I'm going to get that I need my v1, I lost my marker, to equal 0.025 liters. Or that's 25.0 milliliters. This is how much I'm going to need. Both are fine to report in, depending on what the question asks you for unit-wise. So this is how we could take our solution of concentrated HCl and turn it into a 1 molar solution instead. I need to know how much I needed to have. Also from a how would I do this in lab perspective, if I want to go from 25 milliliters to 500 milliliters, that means I'm going to add 475. Now, we'll set it up inside a flask made to hold exactly 500 milliliters. So it's not that you're going to carefully measure out 475. You're going to carefully measure out your 25, put it in a flask made to hold exactly 500, and then fill it up to the line that says this is exactly 500, and then you'll have your new dilute solution. You'll mix it up some. You'll put the top on, shake it some, or however it is you're going to mix it in this case. And now you have 500 milliliters of 1 molar HCl. You're ready to use it for whatever you might need. So that's how we take a concentrated solution and make it dilute. And you can ask for any one of the variables, right? You could say, I've got a concentrated solution, and I add so much liquid. What's the new concentration? That's reasonable. It might be just from the perspective of, oh, I had something that was concentrated, but then I added some water to it, and I want to know what the new concentration was. Maybe I wasn't careful about it, or I wasn't thinking about it. I'm like, I knew I was making it dilute, but I don't know how dilute, so I can figure that out. So any one of those 4 things can be a variable. You just have to know the other 3. And this is when it applies. When I'm doing a dilution, that means that I've got one part of the solution that has stuff dissolved into it, and then I'm adding solvent to it. I'm not adding any more moles, because if I add moles of solute in the second component as well, then it's not a dilution by itself anymore. I mean, could be diluting it, but you can't use this equation because it's not going to apply. This equation assumes you take a concentrated solution and you add a solvent to it, and the moles of the solute do not change. That fact is why this equation works. So with that, hope this will help out. This will be get your equations for dilutions, as well as how to use this with a balanced chemical equation to solve problems. Following up will be a couple of videos where we now start to look at the conceptual part of solutions and what we can do to make predictions of the equations we're working with.